Close your eyes for a moment and picture this. You are standing on the edge of the universe, gazing at a luminous swirl of stars and galaxies scattered like jewels across an infinite canvas. Now, imagine that with just a single step, you could traverse unimaginable distances, crossing light years in the blink of an eye to a world no one has ever seen before. This isn't just the stuff of dreams or science fiction. It's the tantalizing possibility offered by something known as a wormhole. These mysterious cosmic tunnels, hidden deep within the fabric of space-time, could hold the key to unlocking the barriers of vast distances that have kept us confined to our tiny corner of the cosmos. With their allure of instant journeys to far-off galaxies and their potential to completely redefine the way we think about space travel, wormholes serve as a gateway to boundless curiosity and wonder. Tonight, let's embark on a calming, dreamlike voyage into the vast expanse of the universe, where we'll explore the science, the mysteries, and the possibilities of these extraordinary phenomena. As you settle into this relaxing adventure, where are you joining us from, and what time is it there? Share your thoughts below, and let's begin our cosmic journey together. Now turning to the sheer immensity of the universe, let us marvel at its breathtaking enormity. Stretching out in every direction, the cosmos is a tapestry woven with billions of galaxies, each containing billions of stars, planets, and mysteries yet to be uncovered. Imagine light, an ethereal traveler racing at an incomprehensible speed of 300,000 kilometers per second, and yet it would still take it over 100,000 years to cross our own Milky Way galaxy. Beyond that, entire galaxies are scattered like distant islands in a boundless cosmic ocean, separated by millions, sometimes billions, of light years. These distances are so vast that they defy the limits of ordinary comprehension, invoking a sense of awe and humility at our small place within such an infinite expanse. Yet, as awe-inspiring as it is, this vastness presents a monumental challenge to our dreams of exploration. Human ingenuity has gifted us spacecraft that can traverse our solar system, but even the fastest among them would require tens of thousands of years to reach just the nearest star. Our current technology, remarkable as it may be, is acutely limited by these staggering distances, effectively tethering us to the tiny cosmic speck we call home. The idea of exploring far-off galaxies, or even visiting neighboring stars, feels like an impossible dream under these constraints. This is precisely where the concept of wormholes becomes so extraordinary. These hypothetical tunnels through space-time could revolutionize our understanding of distance, offering a way to bypass the daunting stretches of interstellar and intergalactic space. Instead of traveling thousands of years to reach the closest star, a wormhole could potentially make such a journey instantaneous, shrinking the universe in ways that might finally make exploring its furthest corners conceivable. It's a proposition so extraordinary that it has sparked the imagination of scientists and dreamers alike, compelling us to rethink what might one day be possible. With the infinite expanses of the cosmos in mind, let us turn our gaze toward the theories and science that suggest such incredible shortcuts could exist, beginning with the genius who laid the foundation for it all. With the foundation of our journey set, let us now delve into the brilliance of Albert Einstein, whose groundbreaking theory of general relativity reshaped our understanding of the universe and paved the way for the concept of wormholes. Over a century ago, Einstein proposed that gravity is not simply a force pulling objects together, but rather the result of massive objects curving the fabric of space and time itself. Picture the universe as a vast, flexible sheet, like a trampoline. When a heavy object, such as a star or planet, sits on this sheet, it creates a dip, a curve that nearby objects naturally roll toward. This is how Einstein described gravity's profound effect on the cosmos. What's even more astonishing is that space-time, this interconnected framework of space and time, is not fixed. It bends, stretches, and warps, depending on the presence of matter and energy. This idea not only revolutionized physics, but also hinted at extraordinary possibilities. If space-time can bend and warp, could it also fold or connect in unexpected ways? This is where the theoretical notion of wormholes emerges. These hypothetical shortcuts through space-time are imagined as tunnels linking two distant points in the universe, formed by extreme warping of this cosmic fabric. According to Einstein's equations, under the right conditions, such connections could theoretically exist. While Einstein himself did not specifically predict wormholes, his work laid the groundwork for others to build upon. It is this concept of space-time, bending and reshaping, that opens the door to the astonishing possibility of moving through the universe in ways we can barely comprehend. As we continue, let us explore these imaginative ideas further, venturing into the very definition of what a wormhole might be. Now turning to the heart of this fascinating concept, let us uncover what a wormhole truly is. Imagine for a moment that the universe is like a giant piece of paper, stretching endlessly in all directions. On this paper, you have two dots, one representing Earth and the other, a distant star billions of light years away. Normally, traveling from one dot to the other would mean tracing a long, painstakingly slow path along the surface of the paper, requiring unimaginable time and energy. But what if, instead of following that route, you could fold the paper so that the two dots touch? Then, a simple step would take you from one to the other. This is the essence of what wormholes represent, tunnels in the fabric of space-time that could, hypothetically, connect two distant points directly, bypassing the vast stretches of space between them. Envision these wormholes as cosmic shortcuts, much like secret passageways hidden in the universe's design. These theoretical tunnels are not merely a creative idea born out of science fiction. They are grounded in the mathematics of Einstein's theory of general relativity. According to this framework, the warping and bending of space-time create the possibility for such tunnels, offering a way to transcend the colossal distances that make space exploration so difficult. While wormholes remain entirely hypothetical for now, they are imagined as gateways with two openings, each leading to a different point in space, or perhaps even time. To better understand, think of a wormhole as a bridge. Instead of driving the long, winding road that loops around a deep canyon, the bridge allows you to cross directly to the other side. In the same way, A wormhole could link two otherwise distant and unreachable locations in the universe, allowing for nearly instantaneous travel. This idea has captured the imaginations of scientists and dreamers alike, offering a tantalizing glimpse of what might one day revolutionize our understanding of space travel. As we explore further, the question arises, could these shortcuts ever be more than just theoretical? Let us now dive deeper into the science behind wormholes, unraveling the complexities that make their existence both awe-inspiring and an extraordinary challenge for humanity to decipher. As the story of wormholes unfolds further, imagine standing at the edge of a cosmic portal, gazing into the unknown. Visualizing a wormhole can feel like stepping into the pages of a science fiction novel, yet it is a concept deeply rooted in scientific theory. Picture a spherical gateway hovering in the vastness of space, shimmering faintly with a glow that hints at its immense power. Around this gateway, the fabric of space itself seems to ripple and twist, bending light into dazzling, chaotic patterns that defy ordinary perception. The entryway to the wormhole, often called the throat, could appear as a swirling tunnel of energy, leading to a destination far beyond what our eyes could see. To help you imagine this, think of the vivid depictions in movies like Interstellar, where wormholes are shown as three-dimensional spheres rather than flat, two-dimensional circles. This aligns with scientific theories suggesting such a structure might form due to the bending of space-time. Now, let's consider what might happen near this extraordinary phenomenon. The boundary surrounding a wormhole, known as the event horizon, represents a point of no return. It is where gravity becomes so intense that not even light can escape, creating an eerie, pitch-black perimeter. However, unlike a black hole, whose event horizon is a dead end, a wormhole's horizon is thought to serve as a doorway to another part of the universe, or perhaps to a different universe altogether. If light or matter approached a wormhole, its behavior would be nothing short of extraordinary. Light rays might curve and spiral unpredictably, creating stunning visual effects like glowing halos or kaleidoscopic distortions. Matter, on the other hand, would be subjected to powerful forces, potentially stretching and compressing in unimaginable ways as it interacts with the extreme gravitational pull. This interplay of forces and phenomena makes wormholes not only a theoretical marvel, but also an object of immense curiosity for scientists and dreamers alike. While it is one thing to visualize the elegance and mystery of a wormhole, the true challenge lies in understanding whether such entities could ever become navigable. Up next, we will explore the historical roots of wormhole theories, unveiling how great minds of the past brought this idea into the realm of possibility. With the next phase of the journey in sight, let us drift back through the corridors of time to uncover the origins of wormhole theories. It was the early 20th century when Albert Einstein, a name synonymous with unraveling the mysteries of the cosmos, introduced his groundbreaking theory of general relativity. This monumental work revealed that space and time are not separate and rigid entities, but rather a flexible fabric that can bend, stretch, and even fold under the influence of gravity. Decades later, in 1935, Einstein, along with his colleague Einstein-Rosen, ventured further into this cosmic tapestry. Together, they proposed what we now call the Einstein-Rosen bridge, a theoretical construct suggesting that two distant points in space-time could be linked by a tunnel-like structure. This idea laid the foundation for the modern concept of wormholes, merging the worlds of mathematics and imagination in a way that captivated scientists everywhere. As time progressed, other brilliant minds stepped forward to expand on these early ideas. One such figure was the renowned physicist John Wheeler, often remembered as the architect of modern black hole physics. Wheeler coined the term wormhole in the mid-20th century, blending scientific precision with a touch of whimsy to describe these hypothetical shortcuts through the universe. His work helped refine the concept and highlighted the challenges of stability that wormholes would face in the real world. Later, Kip Thorne, a theoretical physicist whose contributions would inspire popular culture, proposed new models for creating traversable wormholes, reigniting interest in their potential for space travel. These pioneers and their bold hypotheses transformed wormholes from a mere curiosity into a serious subject of scientific inquiry, one that continues to evolve to this day. Through the decades of exploration and refinement, the journey of wormhole theories has become an inspiring tale of human curiosity and determination. Each new discovery has added not just complexity, but also a deep sense of wonder about the universe and its hidden pathways. Moving forward, we will delve into the science behind these intriguing phenomena, exploring the principles that might one day make wormholes a navigable reality. Now embarking on a deeper exploration, let us unravel the scientific principles that breathe life into the idea of wormholes. At their core, wormholes are solutions to equations in Einstein's theory of general relativity, a framework that redefined how we understand gravity and the very fabric of our universe. To imagine the possibility of creating or maintaining a wormhole, several strange and fascinating concepts come into play. One of the most critical is the idea of negative energy. Unlike the energy we encounter in our daily lives, which contributes to the gravitational pull between objects, negative energy behaves in the opposite way. It pushes rather than pulls. This peculiar property is believed to be essential for keeping a wormhole stable and preventing it from collapsing under the immense gravitational forces it would naturally generate. Another vital piece of the puzzle is exotic matter. No, this isn't a material plucked from the pages of science fiction, but a theoretical form of matter with properties so unusual that it defies the norms of what we typically understand. Exotic matter is thought to possess negative energy density, enabling it to oppose gravity and hold a wormhole open long enough for anything or anyone to pass through. Without it, most scientific models suggest that a wormhole would be unstable, potentially pinching shut faster than the blink of an eye. Then, there is the sheer scale of gravitational forces involved. Wormholes, if they exist, would likely be surrounded by an environment with extreme gravitational effects, the kind capable of bending and twisting space-time into unimaginable shapes. This immense gravity is both a challenge and a marvel, hinting at the extraordinary physics required to even approach making such a structure a reality. While these ideas might sound complex, What makes them remarkable is how they expand our understanding of the universe and its potential. And so, the science behind wormholes invites us to walk a fine line between the imaginable and the seemingly impossible. With each new theoretical advance, we inch closer to answering the question of whether such cosmic shortcuts could ever be more than just mathematical constructs. Yet, as we delve even further, it becomes clear that creating or finding a wormhole would be one of humanity's most monumental scientific challenges. As we continue this journey, let us examine the distinction between wormholes that could theoretically allow passage and those that remain closed, offering a glimpse into the practical hurdles and wonders that lie ahead. Now turning to the fascinating realm of traversable versus non-traversable wormholes, let us explore the delicate line between theoretical potential and physical limitations. Traversable wormholes are those that, at least in theory, could allow matter, light, or even entire spacecraft to pass through from one point in space to another. They are often imagined as stable tunnels, held open by the elusive exotic matter, creating a bridge through the vastness of space-time. However, this idea, captivating as it may be, is riddled with challenges. Theoretical physics suggests that exotic matter, with its critical role in countering gravitational collapse, would need to exist in quantities we cannot currently produce or even locate. Without it, the immense forces at play would cause the wormhole to collapse in an instant, rendering it non-traversable. On the other hand, non-traversable wormholes, as their name implies, are hypothetical structures that do not permit passage. These could exist due to their inherent instability or the absence of the exotic matter necessary to keep their passageway open. In some models, such wormholes might exist fleetingly, appearing and disappearing before anything could traverse them, while serving only as fascinating yet inaccessible quirks of space-time. The distinction between these two forms is critical, as it draws a boundary between what seems like a cosmic dream and what remains purely within the realm of mathematical imagination. For a moment, let us imagine what exploring a traversable wormhole might feel like. Picture yourself entering a shimmering portal, where the very fabric of space bends and curves around you in ways that defy normal perception. Time itself might seem to slow or distort as you approach the tunnel's event horizon, a threshold that marks the boundary of the wormhole. Inside, the surroundings could appear as a swirling kaleidoscope of light and energy, a visual representation of the immense forces at play. The exit, impossibly distant in ordinary terms, would suddenly be near, delivering you to a new location in the cosmos, as if by an act of pure wonder. Yet, even as we dream of such journeys, the hurdles remain monumental. Stability is not just a question of exotic matter, but of the enormous calculations required to predict and control the behavior of space-time on such scales. Would a traversable wormhole actually stay open long enough for safe passage? Could the immense gravitational forces wreak havoc on anything attempting to travel through it? These are questions that science has yet to answer, reminding us that traversable wormholes remain a tantalizing mystery, balancing on the edge of discovery and impossibility. With these incredible ideas in mind, we inch closer to understanding the profound challenges and promises of wormhole travel. But the mysteries do not end here. Stepping further into the unknown, let us unravel the connection between cosmic strings, those enigmatic relics of the early universe, and their potential role in stabilizing these gateways through space-time. Venturing deeper into the cosmos, let us unravel the enigmatic concept of cosmic strings and their intriguing relationship with wormholes. Imagine these strings as extraordinarily thin, infinitely long threads, remnants from the earliest moments of the universe's creation. While they might sound delicate, cosmic strings are anything but. Packed with immense energy and extraordinary density, they are hypothesized to be defects in the very fabric of space-time, stretching across the universe like ancient scars from its birth. But how do these peculiar structures connect to wormholes? The immense energy of cosmic strings creates an equally immense gravitational pull, capable of bending space-time in profound ways. It is this extraordinary property that has led some scientists to propose that cosmic strings could act as stabilizing agents for wormholes. By anchoring the entrance and exit of a wormhole, they might provide the necessary tension to keep the tunnel open and prevent its collapse under the crushing forces of gravity. Imagine a rope holding open a fragile passage through an otherwise impassable cave. Cosmic strings could perform a similar role, but on a universal scale. Now, picture a scenario where a wormhole is tethered by these cosmic strings. As you approach, you might witness the extraordinary interplay of light bending around the strings, creating a visual effect akin to viewing the universe through a giant magnifying glass. These strings would tether the wormhole, not with physical bonds, but with their intense gravitational influence, creating a dynamic equilibrium between opposing cosmic forces. It is a vision that blurs the line between science and wonder, offering a glimpse into the sheer ingenuity of theoretical physics. Yet, as compelling as this idea may be, it resides firmly in the realm of speculation for now. Cosmic strings, if they exist, are elusive and difficult to detect, leaving their role in wormhole stabilization a tantalizing mystery. Still, the mere possibility that these primordial relics could one day help us unlock the secrets of interstellar travel keeps the imagination alive. With this fascinating interplay of ideas in mind, we turn to the cultural echoes of wormholes, the ways they have captured our collective imagination and inspired visions of what might lie beyond the stars. Now turning to the realm of imagination and storytelling, wormholes have long been a fascinating cornerstone of pop culture, captivating audiences through the magic of movies, television, and books. These depictions often blend scientific theory with creative liberty, sparking curiosity and wonder about the possibilities of the cosmos. Take, for instance, the film Interstellar, which beautifully visualized a wormhole as a shimmering, spherical gateway to another galaxy. The movie not only showcased the theoretical science behind wormholes, but also brought it to life in a way that felt both tangible and awe-inspiring. Similarly, the iconic Star Trek franchise frequently embraced the concept of wormholes, portraying them as vital routes for interstellar travel and exploration, fueling the vision of a connected, expansive universe. In television, Stargate presented a more structured take on wormholes, depicting them as stable portals linking distant planets, navigable through the titular gateway. This series wove the idea into thrilling narratives, blending advanced alien technology with human ambition and curiosity. Such portrayals extend beyond mere entertainment. They inspire viewers to think about the practical and philosophical implications of wormhole travel. Books, too, have played a significant role in cementing the allure of wormholes. Renowned authors like Carl Sagan explored the concept in works such as Contact, where a wormhole becomes the bridge for humankind's first encounter with extraterrestrial intelligence. Through these stories, wormholes transform into symbols of possibility, representing not just shortcuts through space, but also pathways to understanding the unknown. These cultural portrayals serve a dual purpose. They entertain, while also introducing audiences to complex scientific ideas in a way that feels accessible and engaging. Even if the science is sometimes stretched for dramatic effect, the underlying themes ignite a sense of curiosity about our universe and what lies beyond. As wormholes continue to fuel both scientific research and creative imagination, their presence in pop culture ensures they remain a beacon of wonder for generations to come. With this interplay between fact and fiction firmly in mind, let us now explore the practical implications and challenges of using wormholes for faster-than-light travel, a concept that moves us closer to the boundary between what we know and what we dream could be possible. Moving forward into the realm of scientific possibilities, wormholes present an intriguing method for achieving faster-than-light travel, not by defying the universal speed limit set by the speed of light, but by cleverly working around it. Imagine space as a vast, stretched-out fabric. Normally, traveling from one point to another would require moving across this fabric, which could take thousands, even millions of years, even at incredible speeds. Wormholes, however, offer a theoretical shortcut by bending this fabric and connecting two distant points directly. Instead of traveling the long distance across the fabric, you would simply step through the wormhole and instantly emerge at your destination. This concept works within the framework of Einstein's theory of general relativity, which allows for the warping of space and time under extreme conditions. By creating a tunnel through this warped space-time, wormholes could hypothetically provide a route that significantly reduces travel time between 2 points, making interstellar and even intergalactic journeys feasible. The key idea here is that the traveler is not moving through space faster than the speed of light. Rather, they are shortening the distance they need to travel by passing through this cosmic shortcut. This clever circumvention of the speed of light keeps the principles of physics intact while opening the door to astonishing possibilities. Scientists theorize that if a stable wormhole could exist, it might allow for instantaneous travel across vast distances that would otherwise take countless generations. For example, a trip to a distant star system that would typically require tens of thousands of years with conventional propulsion could, in theory, be completed in moments through a wormhole. This has profound implications, not only for human exploration of the universe, but also for the exchange of information, resources, and perhaps even cultures on a cosmic scale. But as fascinating as this concept is, it comes with its own set of monumental challenges, both theoretical and practical. For a wormhole to be traversable, it would need to remain stable long enough for a spacecraft, or even a signal, to pass through. This stability might require exotic matter, a hypothetical form of material with negative energy density, which has yet to be observed or understood. Furthermore, the immense gravitational forces surrounding a wormhole could pose significant risks, potentially tearing apart anything attempting to journey through it. These challenges make the idea of faster-than-light travel through wormholes both tantalizing and daunting, balancing on the fine line between science fiction and revolutionary scientific discovery. As we consider these possibilities, it is impossible not to marvel at the ingenuity of using the universe's own mechanics to dream of traversing it in ways previously thought unimaginable. But the story of wormholes does not end here. With the practical hurdles of building and stabilizing such cosmic phenomena looming large, let us now delve into the immense challenges that lie ahead, obstacles that push the boundaries of human knowledge and ambition. Now turning to the formidable challenges of creating wormholes, we find ourselves venturing into the very edges of human understanding and ingenuity. Theoretical physics tells us that for a wormhole to become a practical gateway through space-time, it would demand an extraordinary set of conditions to exist. First and foremost, the energy requirements to create a wormhole are almost inconceivably vast. To warp space and time to such an extent, we would need a source of energy far beyond anything we can currently produce, perhaps equivalent to the energy of an entire star. Imagine trying to control a power so immense that it dwarfs even the most advanced technologies we possess today. But the need for energy is only the beginning. To keep a wormhole stable and open long enough for anything to pass through, scientists theorize that exotic matter would be required. This is not ordinary matter, like the materials that make up our everyday surroundings. Exotic matter would need to possess negative energy density, a property that has only been observed in fleeting, theoretical scenarios. Negative energy would act as a kind of scaffolding, countering the intense gravitational forces that would otherwise cause a wormhole to collapse almost instantly. However, the nature and behavior of such exotic matter remain one of the greatest mysteries in physics. Nobody knows if it could ever be created or harnessed in a usable form. Even if the immense energy and exotic matter could somehow be obtained, there's the issue of navigating the gravitational tides within a wormhole. These forces could be so extreme and unstable that any spacecraft or signal attempting to pass through might be stretched, compressed, or torn apart before reaching the other side. Designing a mechanism to withstand such forces would require materials and engineering concepts that exist only in the realm of imagination. And then there's the problem of targeting. How would we ensure that a wormhole connects precisely to a desired location, rather than opening up to an unknown and potentially dangerous part of the universe? These obstacles, though daunting, ignite the imagination rather than extinguish it. They represent the kind of challenges that push the boundaries of human ambition and creativity. Each question about wormholes, each unknown variable, serves as a call to explore deeper into the cosmos and to expand our understanding of the fundamental laws that govern reality itself. These hurdles are not the end of the story, but the beginning of a journey that continually tests the limits of what humanity can dream and achieve. With these challenges in mind, the question arises what theoretical models have been proposed to help us better understand, and perhaps one day, conquer the enigma of wormholes. Moving forward, let us journey into the realm of theoretical models that have been proposed to bring wormholes from the abstract into the imaginable. Among the most well-known is the concept of the Schwarzschild wormhole, also referred to as the Einstein-Rosen bridge. This model emerged from the work of Albert Einstein and Nathan Rosen, who mathematically demonstrated that the fabric of space-time could theoretically form a bridge between two separate points. However, there is a catch. Schwarzschild wormholes are believed to be non-traversable, collapsing so quickly that not even light would have time to pass through. They serve as fascinating mathematical constructs, but they lack the stability needed for practical use as cosmic shortcuts. On the other hand, physicists have envisioned models that might allow for traversable wormholes under certain conditions. One such idea is that of thin-shell wormholes, which are theorized as being supported by a boundary of exotic matter. Imagine a delicate bubble that holds the entrance open, allowing for the possibility of passage through to the other side. These thin-shell wormholes would require precise and intricate conditions to remain stable, but they tantalize the mind with the idea that such journeys might one day be achievable. Another intriguing model involves rotating wormholes. In this scenario, the spin creates a stabilizing effect, potentially countering the forces that would otherwise cause the wormhole to collapse. While these rotating wormholes remain purely theoretical, they hint at the complex interplay of motion, gravity, and space-time that could unlock entirely new methods of understanding the universe. Each of these models underscores not only the beauty of physics, but also the boundless creativity of the human mind. They are stepping stones in our ongoing quest to comprehend the mysteries of reality. Though none of these ideas have yet been proven, their existence in theoretical physics inspires both awe and determination. As we continue exploring these possibilities, new questions emerge. Could we go beyond traversable wormholes and imagine even more profound applications, like using them for faster than light travel? The journey deepens as we turn to the theoretical potential of wormholes as cosmic highways, defying the limits of light itself. With the next phase of the journey in sight, let us delve into the question of safety, a vital consideration for any traveler, especially when venturing into something as enigmatic as a wormhole. While the concept of a wormhole conjures visions of instant cosmic travel, the reality of passing through one, if ever possible, may be fraught with its own set of challenges. One of the foremost concerns is radiation. The intense gravitational forces near a wormhole's entrance could generate bursts of high-energy radiation, posing a significant hazard to anything attempting to pass through. Scientists theorize that this radiation could potentially be so powerful that it might destroy matter before it even reaches the other side. Adding to this challenge is the nature of gravity itself. The immense gravitational forces in and around a wormhole might stretch, compress, or even tear apart objects, including a spacecraft, in a process known as spaghettification. This unsettling term paints a vivid picture of what could happen if stability cannot be maintained. Then there is the ultimate uncertainty, what lies on the other side of the wormhole. Theories suggest that it might lead to a distant galaxy, another universe, or perhaps even nowhere at all. What if the destination turns out to be uninhabitable, or a chaotic zone where the laws of physics, as we know them, cease to function? These potential dangers, while sobering, are also what make the idea of wormhole travel so fascinating. They remind us that with great discoveries come great risks, and with each challenge, there lies an opportunity to learn, adapt, and innovate. The unknown nature of wormholes pushes the boundaries of human curiosity, inspiring scientists and dreamers alike to imagine solutions that could one day make such journeys safer. As we ponder these risks, another thought arises: what if their extraordinary potential outweighs the dangers? What if wormholes truly hold the key to unlocking the mysteries of the universe? As the tapestry of possibilities unfolds further, we arrive at a truly mesmerizing concept: time travel. The idea that a wormhole could connect not just two distant points in space, but also two separate moments in time, is perhaps one of the most intriguing implications of these cosmic shortcuts. The theoretical foundation for this comes from the very fabric of space-time itself. According to the principles of general relativity, space and time are not separate entities, but are interwoven, forming a four-dimensional continuum. A wormhole, therefore, might not only bridge vast distances across space, but could also link different eras, functioning as a portal to the past or the future. Imagine, for a moment, being able to step through one end of a wormhole and emerge not just across galaxies, but centuries away from where you began. This would hinge on creating what's known as a time-displaced wormhole, where one end is situated in a different temporal zone compared to the other. Theoretically, such a scenario could be achieved if one mouth of the wormhole were exposed to intense gravitational forces or accelerated to near light speeds, causing time at that end to dilate relative to the other. This phenomenon, known as time dilation, is a well-documented effect in physics, but integrating it into a stable wormhole design remains speculative. Of course, as captivating as this vision may be, it raises profound questions about causality, our basic understanding of cause and effect. If someone were to use a wormhole to travel back in time, they might theoretically alter events in ways that ripple forward, potentially reshaping the future they came from. This gives rise to paradoxes, like the famous grandfather paradox, where a time traveler's actions might prevent their own existence. On the other hand, some theories suggest that the universe may have built-in mechanisms, such as the concept of self-consistency, ensuring that any actions taken in the past would align with the timeline as it already exists. While these ideas remain largely in the realm of theoretical physics and science fiction, they stimulate not only scientific exploration, but also philosophical inquiry. Could wormholes allow us to observe history firsthand, or even safeguard humanity by altering a catastrophic chain of events? Or would their misuse introduce unpredictable chaos? The answers, much like wormholes themselves, remain shrouded in mystery, yet they continue to ignite a profound sense of wonder. With this exploration of time travel, we find ourselves peering into a realm where the boundaries of possibility blur, leading to the next profound question: how close are we to uncovering evidence of wormholes in the cosmos? Now turning to the fascinating pursuit of discovery, let us explore how scientists are tirelessly searching for evidence of wormholes in the cosmos. This quest begins with the understanding that wormholes, if they exist, would leave behind subtle yet detectable imprints on the fabric of space-time. Astrophysicists often rely on the study of gravitational waves, those ripples in space-time caused by cataclysmic cosmic events like the collision of black holes. If a wormhole were involved in such an event, its unique signature might reveal itself in the patterns of these waves, offering a tantalizing clue of its presence. Another approach involves scanning the universe for peculiar phenomena that defy explanation under known physical laws. For instance, scientists investigate anomalies in light emitted or bent around massive objects, known as gravitational lensing. If a wormhole were positioned between Earth and a distant star, it might distort the light in a way that differs from ordinary gravitational lensing caused by objects like black holes or galaxies. Such an observation could provide indirect evidence of a wormhole's existence. There is also the exciting prospect of searching for what are called shadow objects, a phenomena that could represent the openings of wormholes. With advancements in high-resolution telescopic imagery, such as that used to capture the silhouette of a black hole, researchers are now looking more closely at regions of space with unusual energy distributions or unexpected behaviors. These could serve as potential markers of a wormhole's presence, awaiting further investigation. Adding to the toolkit, we have computer simulations and artificial intelligence. By modeling the extreme conditions of space-time under hypothetical wormhole scenarios, scientists can create predictive frameworks to guide observation strategies. Artificial intelligence is particularly invaluable, scouring through vast amounts of astronomical data to pinpoint anomalies that might otherwise escape human notice. While the search remains in its infancy, each new piece of data fuels the hope that evidence may be just within reach. Could a faint gravitational wave, an odd flicker of light, or an unusual data anomaly be the long-sought key to finding these theoretical passageways? The answers remain elusive, but with each advancing technique, humanity inches closer to unraveling this cosmic mystery. As we uncover these groundbreaking methodologies, it becomes clear that our fascination with wormholes is not just rooted in theory. It is actively shaping the future of scientific exploration. This relentless pursuit of understanding naturally leads us to examine a closely related enigma: the potential connection between black holes and wormholes. Delving deeper into the mysteries of the cosmos, we arrive at the captivating interplay between black holes and wormholes. Black holes, with their immense gravitational pull, are often regarded as gateways to the unknown. These enigmatic regions of space, where gravity is so intense that not even light can escape, have inspired countless theories. Among them is the tantalizing idea that black holes might be linked to the formation of wormholes. Some physicists propose that under the right conditions, The extreme gravitational environment near a black hole could warp space-time to such an extent that it creates a bridge, a wormhole, connecting 2 points in the universe. This fascinating concept stems from solutions to Einstein's equations of general relativity, which not only allow for black holes, but also suggest the theoretical possibility of wormholes as shortcuts through space-time. What makes this connection even more intriguing is the hypothesis that certain types of black holes, particularly rotating ones known as Kerr black holes, might possess environments conducive to forming or sustaining a wormhole. The rapid spin of these black holes could, in theory, stabilize the tunnel-like structure of a wormhole, preventing it from collapsing under the immense forces at play. This idea sparks curiosity about whether such stable wormholes could exist naturally, or if they are purely products of mathematical imagination. Beyond the science, there is an undeniable allure to the visual and conceptual beauty of these celestial phenomena. Picture the swirling accretion disk of a black hole, glowing with energy as it pulls in nearby matter. Now imagine the possibility that within this dramatic cosmic ballet lies a passage to an entirely different corner of the universe. It is both awe-inspiring and humbling to consider that such extraordinary structures could hold the keys to unlocking the secrets of interstellar travel. While the connection between black holes and wormholes remains theoretical, the intersection of their mysteries continues to fuel scientific exploration and philosophical wonder. Could a black hole truly serve as the entrance to a wormhole, or are these ideas destined to remain a thought experiment? As we ponder these questions, it becomes clear that understanding the relationship between black holes and wormholes is not just about physics. It is about pushing the boundaries of human imagination. This journey inevitably leads us to the fascinating realm of quantum mechanics and its speculative ties to wormholes. With the next phase of the journey in sight, we enter the ethereal world of quantum mechanics, a realm that challenges our very understanding of reality. Here, at the smallest scales of existence, particles behave in ways that defy intuition, seemingly connected across vast distances in phenomena known as quantum entanglement. This strange interconnectedness, where two particles can influence each other instantly regardless of the space between them, sparks a fascinating question. Could this mysterious link offer clues about the nature of wormholes? Some physicists speculate that quantum entanglement and wormholes might be two sides of the same cosmic coin. Imagine two particles separated by light years, yet acting as if they are in direct contact. Now envision a hidden thread, or perhaps a tiny wormhole, connecting these particles through an invisible bridge in space-time. Could it be that entanglement, often described as spooky action at a distance, is evidence of a deeper connection, one that mirrors the theoretical pathways of wormholes? This idea connects to a concept known as the Einstein-Rosen bridge, which suggests that wormholes could be the quantum counterpart to entangled particles. If true, it might mean that wormholes exist not just as shortcuts for objects, but also as conduits for the very fabric of quantum information itself. Such a possibility redefines not only how we see the cosmos, but also how we imagine traveling through it, While the relationship between quantum mechanics and wormholes remains speculative, one can dream of the profound implications. Picture using these quantum bridges to communicate instantly across galaxies, bypassing the delays of light speed limitations. Perhaps these connections could even illuminate deeper truths about the universe's structure, unraveling mysteries that lie far beyond our current comprehension. Considering these ideas brings us closer to the dreamlike potential of wormholes, bridging not just space, but also the divide between theory and imagination. As we delve deeper into the interplay of quantum mechanics and the cosmos, we are reminded of the boundless creativity inherent in exploring the unknown. This boundless curiosity naturally leads us to examine practical applications and the tantalizing possibilities wormholes could unlock for the future. As we venture further into the horizon of possibility, let's imagine a future where wormholes are no longer just theoretical wonders, but tangible gateways reshaping our existence. Picture a scenario where interstellar travel becomes as routine as a short flight across continents, a journey not measured in centuries but in moments. With the ability to leap across the galaxy through these cosmic shortcuts, entire new worlds teeming with unknown resources and breathtaking landscapes could become accessible. Colonizing distant planets might shift from being a distant dream to an imminent reality, offering solutions to Earth's growing challenges like overpopulation and resource depletion. But the potential applications do not end there. Envision a system where resource transport is revolutionized, not merely across countries, but literally across galaxies. Precious elements or vital materials from planets light years away could be delivered instantaneously, fueling innovation and creating opportunities on scales previously unimaginable. Beyond physical goods, think of the extraordinary implications for communication. Instead of relying on radio waves that take years to traverse vast interstellar distances, wormholes could serve as instantaneous conduits. Communication delays would vanish, enabling humanity to connect and collaborate across the stars in real time, fostering an unprecedented era of intergalactic unity and understanding. This technology could also pave the way for scientific advances that transcend our current comprehension. Access to previously unreachable regions of the universe could offer answers to age-old questions about the origins of life and the cosmos itself, sparking a golden age of discovery. The boundless curiosity and ingenuity of humans might even transform wormhole travel into a tool that brings disparate civilizations together, bridging cultures and fostering universal collaboration. As these visions take shape, they inspire a profound sense of wonder about what humanity could achieve if such potential were unlocked. While the practical realization of wormholes remains an immense challenge, dreaming of their possibilities keeps our eyes fixed on the stars and our minds open to the infinite. This exploration of what could be lays the foundation for even deeper questions as we prepare to examine the ethical and philosophical implications of such transformative technology in our journey ahead. As the next phase of our journey unfolds, we turn our attention to the profound ethical dilemmas that the advent of wormhole travel could introduce. The idea of wielding the power to traverse galaxies in an instant sparks as much concern as it does excitement. A central question emerges: who would hold the authority over such a game-changing technology? Would it be entrusted to nations, private corporations, or a unified global entity? The answer to this could shape the future of humanity in unpredictable ways. If monopolized by a select few, wormhole travel could deepen existing inequalities, granting unimaginable power and access to resources to certain groups while leaving others behind. On the other hand, shared stewardship could foster collaboration, yet it would require unprecedented levels of global trust and cooperation. Beyond control, there lies the question of intention. How would this technology be used? Could wormholes become tools of exploration and unity, or might they serve more destructive purposes? The potential for misuse in the wrong hands cannot be ignored, and safeguards would need to be carefully designed to prevent catastrophic outcomes. Additionally, the environmental and cosmic consequences of manipulating the fabric of space-time must be considered. Would creating and using wormholes upset the delicate balance of the universe, triggering unforeseen events? Could such interference pose risks not just to our world, but to other parts of the cosmos? Another layer of complexity arises when we think about the impact on cultural and philosophical perspectives. If wormhole travel connects humanity to alien civilizations or even parallel universes, how would this challenge our sense of identity and place in the universe? These encounters might foster understanding and growth, but they could also give rise to conflicts over differing values, perspectives, and intentions. The sheer magnitude of such interactions could reshape the foundations of human thought and society in ways we are barely equipped to predict. Ultimately, the ethical implications of wormhole travel push us to reflect deeply on what it means to wield such extraordinary power. It demands that we not only advance scientifically, but also grow in wisdom and responsibility as a species. Without careful thought and planning, the very technology that promises to unite and uplift us could become a force that divides or endangers. With these questions in mind, we continue to explore, delving into how alien civilizations might already be using such technology and what that could mean for humanity's place in the ever-expanding tapestry of the universe. As we venture further into the depths of our imagination, we encounter the tantalizing possibility that advanced alien civilizations might already possess mastery over wormhole technology. For beings with lifespans, intellects, and resources far beyond our own, the development of such travel could be as fundamental to their existence as the invention of the wheel was to our ancestors. If alien species are indeed navigating vast cosmic distances through these mysterious gateways, what stories might each wormhole whisper of their journeys, their civilizations, and their purposes? The implications of such mastery are profound. On one hand, the existence of alien travelers harnessing wormholes could signify incredible advances in cooperation, knowledge, and technological evolution. It might suggest a collective ability to balance power with responsibility in ways humanity is still striving to achieve. But on the other hand, the This raises questions about their intentions and the role humanity might play in their broader interstellar narrative. Would such advanced entities view us as equals, mere spectators, or even obstacles in their exploration of the cosmos? The potential meeting of civilizations across a wormhole introduces both hope and caution. Such an encounter could bring boundless opportunities to learn, to grow, and to understand the universe from perspectives we can scarcely imagine. However, it could also lead to tension, as differing values, priorities, and objectives collide. In a universe where resources, even on a cosmic scale, might be finite, how would humanity negotiate its place amidst more advanced beings? Furthermore, these civilizations might possess knowledge that challenges everything we think we understand about existence, about physics, biology, and even consciousness itself. Could we, as a species, stand ready to absorb such revelations without being overwhelmed by their magnitude? Or would their discoveries prompt us to reevaluate our sense of identity and purpose on both individual and collective levels? What if the very fabric of our understanding of time, dimensions, and reality were reshaped by what they reveal? It's also worth considering whether wormholes, in the hands of these civilizations, serve purposes far beyond mere transportation. Could they function as tools for communication across unimaginable distances, or even as conduits for energy or information transfer? Might they be part of a galactic framework that links countless worlds, creating a kind of cosmic infrastructure that operates on a scale we can barely begin to perceive? These possibilities stretch the boundaries of our imagination, but they also challenge us to think critically about how we would respond to such a reality. If these civilizations have mastered wormhole technology, then perhaps their existence might serve as a road map proof that the obstacles we face in pursuing such advancements are not insurmountable. At the same time, it reminds us that with great power comes an even greater responsibility, not only to ourselves, but to the cosmos at large. With these considerations in mind, we step further into the unknown, exploring how wormholes could also connect us not just through space, but perhaps even through time itself, forever altering the way we perceive our place in the universe. With our imagination carrying us further into the vast possibilities of the cosmos, we now explore an even more enthralling notion: wormholes as gateways to parallel universes. This concept, long a favorite in the realm of science fiction, invites us to consider realities that exist beyond the one we know. Imagine a wormhole not just as a shortcut connecting two points in space, but as a bridge between entirely different dimensions, where the rules of physics, time, and even life itself could differ in ways that defy our understanding. Such an idea has ignited countless stories in books, movies, and television, each offering unique interpretations of what lies on the other side. Whether it's alternate Earths in popular films or the mesmerizing multiverses in novels, these narratives have shown us worlds where history took a different path. Choices led to divergent outcomes, and life evolved in entirely unexpected ways. Beyond storytelling, this possibility raises profound scientific and philosophical questions about the nature of existence itself. If wormholes could connect us to parallel universes, then could there be other versions of ourselves living out different lives. Could these alternate realities hold solutions to problems we face in our own universe, or even risks we could scarcely predict? This theory challenges the boundaries of what we consider real, expanding our perspective of existence to possibly include infinite variations of space, time, and consciousness. Yet, while these ideas inspire wonder, they also remind us of the limits of our current understanding. How would such connections work? Could they ever be stable enough to explore? And if we did find a way to traverse these cosmic bridges, would we be prepared for what we might encounter? These are questions that stretch the imagination, but they also encourage us to remain curious and hopeful about uncovering the deeper truths of the universe. As we marvel at these possibilities, we also prepare to delve into another fascinating idea: the potential relationship between wormholes and black holes, exploring how these enigmatic phenomena might intersect in the fabric of space-time. With the next phase of the journey in sight, we turn our attention to the brilliant mind of Stephen Hawking and his thought-provoking perspectives on wormholes. Known for his groundbreaking contributions to theoretical physics, Hawking often explored ideas that stretched the boundaries of our understanding, and wormholes were no exception. While he recognized the tantalizing potential of these cosmic pathways, his insights were tempered with caution. Hawking delved into the paradoxes and challenges that wormholes might present, particularly regarding their stability and feasibility for travel. One of his key concerns was the instability of a wormhole itself. He theorized that even the slightest disturbance, such as the passage of a single particle, could cause these structures to collapse almost instantly. For a wormhole to remain open and traversable, it would likely require something known as exotic matter with negative energy density, a substance that remains purely theoretical to this day. Moreover, Hawking highlighted the potential for paradoxes, particularly those involving causality and time travel. If a wormhole connected 2 points in space-time, possibly even 2 moments in time, it could create scenarios where the very laws of cause and effect might unravel. He considered whether such paradoxes would fundamentally conflict with the principles that govern our universe, raising the question of whether the universe itself might have mechanisms to prevent such phenomena. Despite these challenges, Hawking's exploration of wormholes was not without hope. He recognized that these enigmatic structures could offer profound insights into the nature of space, time, and the boundaries of human understanding. In many ways, his work encouraged us not only to dream of the possibilities, but also to confront the limitations and questions that come with them. As we reflect on Hawking's cautious yet inspiring views, we are reminded that the pursuit of knowledge often resides at the intersection of curiosity and skepticism. This delicate balance invites us to imagine boldly while remaining grounded in scientific inquiry. With these thoughts in mind, let us now venture into another intriguing connection: the relationship between wormholes and the mysterious depths of black holes, exploring how these phenomena might intertwine within the tapestry of the universe. Now venturing into the exciting realm of possibilities, let us consider the question: could humanity ever build a wormhole? This concept, seemingly plucked from the pages of science fiction, inspires both awe and intrigue. The idea of artificially creating a gateway through space-time requires us to imagine technology far beyond what exists today. At its core, constructing a wormhole would involve manipulating the fabric of the universe itself, a feat that demands advances so profound they currently reside in the realm of speculation. Scientists theorize that to form a stable wormhole, we would need an immense amount of energy, possibly equivalent to that of an entire star. This energy would need to bend and twist space-time, creating the tunnel-like structure that connects two distant points in the cosmos. But that is only the beginning. To keep a wormhole open for traversal, exotic matter with negative energy density, a substance we have yet to discover, would likely be required. Without it, the intense gravitational forces surrounding the wormhole would cause it to collapse faster than anything or anyone could pass through. Despite these challenges, the idea of creating a wormhole is not entirely out of reach. Researchers continue to explore theoretical models that might one day guide us in achieving such an ambitious goal. Innovations in quantum mechanics, advanced materials, and energy generation could hold the key to unlocking this mystery. Imagine a future where a new scientific breakthrough allows us to harness the immense forces of the universe, where theories once constrained to mathematical equations become tangible realities. While the road to constructing a wormhole is undoubtedly steep and uncertain, the pursuit itself reflects the boundless curiosity and determination that define us as a species. Each small step forward in understanding the universe brings us closer to realizing what now seems impossible. As we dream of shaping space-time to our will, we are reminded that the journey of discovery often begins with bold questions. And so, as we ponder the prospect of building a wormhole, we find ourselves gazing not just outward toward the stars, but inward at the extraordinary potential of human ingenuity. As the next frontier of exploration comes into view, let us consider the transformative role of artificial intelligence in unlocking the mysteries of wormholes. Artificial intelligence, with its ability to process vast amounts of data and identify patterns far beyond human capabilities, could revolutionize how we study and potentially create these enigmatic structures. Imagine a system capable of simulating the intricate laws of physics that govern the universe, mapping out the complex interplay of gravitational forces, energy fields, and space-time distortions. Artificial intelligence models, designed to delve into the depths of these calculations, could help scientists explore theoretical possibilities with an unprecedented level of precision and efficiency. For instance, by simulating scenarios that involve exotic matter or the extreme conditions required to form a wormhole, artificial intelligence can test hypotheses and refine models without the constraints of physical experiments. Beyond theoretical simulations, artificial intelligence could also play a pivotal role in detecting the existence of wormholes in the cosmos. By analyzing massive data sets from telescopes and other observational tools, artificial intelligence could identify anomalies that might hint at space-time distortions caused by a wormhole. These subtle clues, perhaps hidden within the noise of the universe's vast expanse, would be nearly impossible to detect without the speed and accuracy of artificial intelligence systems. Moreover, Artificial intelligence might assist in engineering advancements by optimizing the design and functionality of futuristic devices capable of manipulating gravitational or quantum forces. By integrating artificial intelligence into this process, researchers could accelerate progress and explore solutions that might otherwise take generations to uncover. In many ways, artificial intelligence serves as an extension of human curiosity and determination, bridging the gap between theory and discovery. While artificial intelligence on its own cannot create wormholes, its ability to simulate, analyze, and interpret complex phenomena makes it an invaluable ally in this journey of exploration. As we harness the potential of artificial intelligence, it becomes clear that the path to understanding wormholes is not one we walk alone. It is a collaborative dance between human ingenuity and technological innovation, bringing us closer to unraveling the secrets of the cosmos. What lies ahead remains uncertain, but the incorporation of artificial intelligence into this grand quest reminds us that the future of science is as much about collaboration as it is about curiosity. And speaking of curiosity, it leads us to wonder how wormholes might revolutionize our understanding of faster-than-light travel. Let us move forward and delve into this fascinating possibility. As we journey deeper into the mysteries of the universe, let us turn our attention to the profound impact wormholes have on expanding human perspective. Even as theoretical constructs, wormholes compel us to rethink the very fabric of reality and challenge the limits of what we believe to be possible. They invite us to see the universe not as an insurmountable expanse, but as a realm of infinite possibilities, where distance and time might someday bend to human ingenuity. The idea of wormholes stirs the imagination, encouraging scientists, artists, and dreamers alike to envision a cosmos where the barriers of space-time are no longer constraints, but opportunities for exploration and discovery. For scientists, the concept of wormholes opens new frontiers in theoretical physics, requiring advancements in our understanding of gravity, quantum mechanics, and the nature of energy. For artists and storytellers, wormholes serve as gateways to boundless creativity, inspiring tales that stretch the limits of human experience. Consider how the contemplation of these space-time tunnels might reshape our view of existence. They push us to think beyond our immediate world, fostering a sense of connection to something far greater than ourselves. They remind us of the vastness of the cosmos and the ingenuity required to explore it, fueling the ambition to reach beyond what current technology and knowledge allow. Moreover, wormholes ignite a sense of wonder that transcends scientific curiosity. They remind us that the universe is a place of extraordinary mysteries, filled with phenomena that defy simple explanation. This sense of wonder is not just an abstract feeling. It drives innovation, influencing fields as diverse as engineering, energy research, and artificial intelligence. By inspiring us to tackle challenges that once seemed insurmountable, wormholes exemplify how theoretical ideas can lead to practical advancements, ultimately enriching our understanding of the universe and our place within it. And as we marvel at these possibilities, we prepare to explore their connection, not just to space travel, but to the very fabric of time itself. Let us journey next into the fascinating realm of how wormholes might unlock the mysteries of time travel. As the next chapter unfolds, close your eyes and imagine yourself standing at the edge of a shimmering cosmic portal, a wormhole twisting and curving before you like a cascade of starlight, swirling into infinity. The space around it feels alive, humming with a gentle, otherworldly energy that vibrates through your very being. You take a step forward, and as you cross the threshold, the fabric of reality itself seems to stretch and flow around you. Suddenly, you are gliding effortlessly through the tunnel of the wormhole, enveloped in a luminous brilliance that pulses with countless hues, colors beyond description that seem to sing softly as they swirl around you. There's no sense of gravity, no weight or resistance, only the soothing sensation of movement, as if you're floating gently on a cosmic breeze. The tunnel expands and contracts rhythmically, as though breathing, and you notice faint, fleeting glimpses of galaxies, stars, and otherworldly vistas, shimmering just beyond the edges of this glowing pathway. Time itself feels unfamiliar here, not rushing, not slowing, but an eternal, tranquil now. The worries of the world fade away, replaced by an overwhelming sense of peace and wonder. It's as if you've become one with the universe, a silent traveler in a realm unbound by the constraints of space and time. As you drift further, there is an overwhelming sense of connection. The wormhole feels less like a passage and more like a bridge, linking the farthest reaches of the cosmos. You can almost feel the pull of distant stars beckoning you, inviting you to explore worlds and dimensions beyond imagination. It's a journey not just across space, but through the core of existence itself, a reminder that the universe is vast, mysterious, and full of possibilities yet to be discovered. And as you emerge from this radiant tunnel into a new corner of the cosmos, the journey lingers within you, sparking a sense of purpose and curiosity. The questions left behind are not burdens but gifts, igniting the dream of exploration, of venturing farther, of discovering what lies beyond the next horizon. Such meditations remind us of why we look to the stars, to seek, to wonder, and to unravel the mysteries of existence. And just as wormholes may connect distant points in space, they also connect us with our own limitless imagination. With this vision in mind, let us now explore the obstacles and challenges that must be overcome before such extraordinary journeys can transform from dream to reality. With the next phase of the journey in sight, let us consider the monumental challenges that stand between us and the reality of wormhole travel. Scientifically, the concept of wormholes demands a deep understanding of the universe's most complex principles. These theoretical shortcuts through space-time, while fascinating, require exotic matter, a substance with negative energy density that has yet to be observed or created. Without exotic matter, keeping a wormhole stable enough for travel seems impossible, as ordinary matter would cause it to collapse almost instantly. Technologically, the energy requirements for creating or sustaining a wormhole are beyond anything humanity can currently achieve. To open even a tiny wormhole, the amount of energy needed would dwarf anything produced by our most advanced systems, rivaling the power of stars themselves. Our current technology is in its infancy compared to what would be necessary to manipulate space-time on such a grand scale. Understanding and harnessing this level of power is a puzzle we have only begun to approach. Then there are the ethical questions, which are just as significant as the scientific ones. If wormhole travel became possible, who would control such a transformative technology? How would it be used, and could it create inequalities or conflicts among nations and peoples? Additionally, the potential for unintended consequences, disruptions to the fabric of space-time, or effects on distant regions of the cosmos, poses dilemmas that require careful consideration. Would humanity use this power responsibly, or could it lead to unforeseen dangers? Yet despite these obstacles, the dream of wormhole travel endures. Each challenge is not a barrier, but an invitation to innovate, to push the boundaries of what we know and what we can achieve. History has shown us that humanity's resilience and curiosity are unmatched. From harnessing fire to exploring the depths of the oceans and the vastness of space, we have always risen to meet the unknown with ingenuity and determination. Though wormholes remain a distant possibility, they remind us of the limitless potential of human imagination and the incredible journey that lies ahead. Perhaps through persistence and collaboration, tomorrow's impossibilities will become realities, urging us ever forward into the mysteries of the universe. As we set our sights on the horizon of possibility, the promise of continued research into wormholes and space-time offers a beacon of hope for unraveling the universe's most profound mysteries. Around the world, scientists are pushing the boundaries of theoretical physics, striving to better understand the principles that could make wormholes a reality. Universities and research institutions are delving into the complexities of space-time, exploring concepts like quantum mechanics, gravitational waves, and the exotic particles that might hold the key to stabilizing these extraordinary passages. Their work represents the cutting edge of human curiosity, forging new paths in our quest to unlock the secrets of existence. Government agencies and private organizations are also playing crucial roles in this cosmic exploration. For example, space programs are investing in advanced telescopes and observational technologies, examining the universe for signs of phenomena that could hint at the existence of wormholes. These tools help us detect subtle distortions in space-time that could provide clues, even if indirect, about their presence. Meanwhile, particle accelerators and experiments in quantum field theory are expanding our understanding of the fundamental forces that govern the cosmos, taking us one step closer to bridging the gap between theoretical models and tangible evidence. Collaboration is emerging as a key element in these efforts, as scientists across disciplines and borders come together to tackle the immense questions posed by wormholes. By pooling knowledge, resources, and perspectives, the global scientific community is creating a foundation for discoveries that could transform our understanding of the universe. Breakthroughs in related fields such as artificial intelligence and computational modeling are further empowering researchers to simulate complex scenarios, unraveling the intricate dynamics of space-time and the extraordinary conditions required to form and maintain wormholes. While the journey is still in its early stages, each new study and experiment brings us closer to answers, These efforts not only fuel our intellectual curiosity, but also remind us of the boundless potential of collective human endeavor. The exploration of wormholes is not just a scientific pursuit, it is a testament to our enduring desire to understand our place in the vast landscape of the cosmos. With so many dedicated minds working tirelessly to illuminate the unknown, the possibilities for future discoveries are as infinite as the universe itself. As we draw this journey through the cosmos to a close, the wonder and potential of wormholes continue to captivate our imaginations. These theoretical gateways, with their promise of bounding across the universe in the blink of an eye, remind us of the uncharted possibilities that lie ahead. Even though the path to making wormholes a reality is filled with challenges, it is this very pursuit that embodies the human spirit, our endless curiosity, our drive to explore, and our yearning to transcend the limits of what we know. The dream of faster space travel is far from just a scientific endeavor. It is a shared vision that unites scientists, dreamers, and everyone who dares to look up at the night sky and wonder what lies beyond. So, as you drift back into the rhythm of your day, hold on to this sense of wonder. Keep imagining the incredible possibilities that the universe holds for us. If you enjoyed venturing into these cosmic ideas, don't forget to like, subscribe, and hit the notification bell to join us on more journeys into the mysteries of existence. Thank you for watching, and keep dreaming of the stars.